Welcome to True Projects. In this video, we are going to explain about the project titled Design of Deep Learning Models for the Identifications of Harmful Attack Activities in IIoT. Introduction. The project focuses on developing sophisticated deep learning models specifically tailored for detecting and identifying malicious activities within Industrial Internet of Things IIoT systems. These models leverage complex algorithms to analyze data and patterns, aiming to differentiate between normal system behavior and potentially harmful actions. Industrial Internet of Things IIoT refers to the interconnectedness of physical devices, machinery, and systems within industrial settings. It involves the integration of sensors, software, and other technologies to enable data exchange and automation, bridging the gap between the digital and physical worlds in industries like manufacturing, logistics, and energy. IIoT systems are susceptible to cyber attacks due to their interconnected nature. These attacks can exploit weaknesses in the system, potentially causing financial losses and reputational damage for businesses. The diverse range of interconnected devices and the interplay between software and hardware components create various entry points for malicious actors. While Network Intrusion Detection System (NIDS) are recommended for safeguarding IIoT systems, identifying both known and novel attack patterns poses a significant challenge. Traditional methods struggle to keep pace with evolving attack strategies, making it difficult to detect and mitigate sophisticated and previously unseen threats effectively. To address the limitations of existing security measures, the project proposes the implementation of an anomaly recognition system. This system utilizes advanced deep learning algorithms capable of analyzing TCP or IP packet data, which is crucial for network communication. By employing deep learning techniques, the system aims to learn normal patterns and deviations, enabling the identification of potential threats or anomalies that diverge from expected behavior within the IIoT network. Objective. The primary aim of this project is to create specialized deep learning models tailored explicitly for identifying and mitigating harmful attacks within Industrial Internet of Things IIoT systems. These models are intended to enhance the security infrastructure of IIoT environments by effectively recognizing and responding to potential threats. The project focuses on developing an anomalies recognition system using advanced deep learning algorithms. The objective is to equip this system with the capability to not only detect known attack patterns but also effectively identify novel, previously unseen attacks within IIoT systems. This approach ensures a proactive defense mechanism against evolving threats. The project employs sophisticated deep learning architectures like deep autoencoders and feed-forward neural networks to process and analyze data obtained from TCP or IP packages. These neural network designs are trained to understand and differentiate normal network behavior from potentially malicious activities, thereby enhancing the system's ability to identify threats accurately. To validate the efficacy of the developed models, the project uses established and widely recognized network datasets such as NSL-KDD and UNSW-NB50. These datasets serve as benchmarks for training and evaluating the deep learning models, allowing for rigorous testing and comparison against existing methodologies. The project's ultimate goal is to demonstrate the proposed methodology outperforms previous approaches by achieving a lower false positive rate and higher detection accuracy. By showcasing superior performance metrics, the aim is to illustrate the suitability and effectiveness of the developed models in real-world IIoT scenarios. This validation can potentially lead to increased trust and adoption of these models within industrial settings for enhanced security measures. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8GB and above, hard disk of 25GB and above. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, backend framework is Jupyter Notebook. Database is SQLite 3. Front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. In this initial phase, various Python packages and libraries are imported to facilitate data handling, analysis, and deep learning model development. Commonly used packages include Pandas for data manipulation, Keras for building neural networks, and potentially others like NumPy for numerical operations and Matplotlib for data visualization. Exploring the dataset. The project involves the exploration of multiple datasets relevant to Industrial Internet of Things, IIoT security. NSL-KDD, a well-known dataset used for evaluating intrusion detection systems containing various types of attacks and normal network traffic. UNSW-NB15, another dataset widely used for network security research, featuring a variety of cyber attacks and normal traffic instances. Bot IoT, possibly a dataset specific to IoT botnet attacks, focusing on IoT device compromises and the network behavior. MQTT IoT, potentially a dataset related to MQTT, message queuing, telemetry transport, protocol-based IoT devices, showcasing the network activities. Data processing, Pandas data frame. Utilizing Pandas, the datasets are organized into data frame structures, enabling efficient manipulation and analysis of the data. Keras data frame. While Keras primarily deals with neural network construction, it's likely used to format the data into suitable structures for training deep learning models. Dropping unwanted column. Irrelevant or redundant columns within the datasets are removed to streamline the data and focus on pertinent features for the deep learning models. Converting binary class. This step involves converting categorical or multi-class data, example types of attacks, into a binary format suitable for binary classification tasks, distinguishing between normal and malicious activities. Visualization using Seaborn and Matplotlib. Seaborn and Matplotlib are utilized to visualize and understand the data. They offer various plotting functionalities to create insightful visual representations such as histograms, heat maps, scatter plots, etc., helping in the exploration and analysis of dataset characteristics, distributions, and relationship between variables. Label encoding using label encoder. Label encoder, likely from the sklearn library, is employed to convert categorical data or textual labels into numerical representations. This pre-processing step assigns unique numerical values to categorical labels, enabling the machine learning model to interpret and process them effectively. Feature selection. Select percentile using mutual info classify. Select percentile coupled with mutual information classification is used for feature selection. This technique ranks and selects the most informative features based on their mutual information with the target variable. It helps in reducing dimensionality and focusing on the most relevant features for model training. Splitting the data to train and test for deep learning. The dataset is split into training and testing subsets. This step ensures that the deep learning model is trained on one portion of the data and evaluated on another, helping to assess its performance and generalization capabilities. Building the model. This stage involves the construction of a deep learning model architecture using frameworks like Keras or TensorFlow. The model's layers, activation functions, loss functions, optimizers, and other parameters are defined to create a neural network suitable for detecting harmful attacks in IIoT systems. Training the model. The constructed deep learning model is trained using the training dataset. During this phase, the model learns to recognize patterns and features in the dataset related to attack activities, adjusting its parameters through multiple iterations to minimize the defined loss function. Flask framework with SQLite for sign-up and sign-in. Flask, a Python web framework, is integrated with SQLite, a lightweight relational database. This combination is used to implement user authentication functionalities such as sign-up and sign-in, allowing authorized access to the system. User gives input as feature values. Users provide input in the form of feature values related to IIoT system activities or network behavior. The given input is pre-processed for prediction. The received user input undergoes pre-processing steps similar to those applied to the training data, ensuring it's in a suitable format for prediction by the trained model. Trained model is used for prediction. The pre-processed input is fed into the trained deep learning model, which makes predictions or classifications regarding the nature of the input data, identifying potential harmful attack activities in the IIoT system. Final outcome is displayed through front end. The prediction outcomes or model results are displayed to the user via a front-end interface, providing insights into the likelihood of the input data representing harmful attack activities within the IIoT system. Algorithms used in this project, we have utilized the following algorithms. The first one is Deep Feed Forwarding Neural Network DNN. A deep feed-forward neural network, also known as feed-forward neural network or a multi-layer perceptron MLP, is a type of artificial neural network where information moves in one direction forward. It consists of an input layer, one or more hidden layers, and an output layer. Each layer contains nodes, neurons interconnected by weights. These networks are used for supervised learning tasks like classification and regression. Autoencoder DNN. An autoencoder is a type of neural network used for unsupervised learning. It consists of an encoder and a decoder. The encoder compresses the input data into a lower dimensional representation, and the decoder attempts to reconstruct the original data from this representation. Autoencoders are used for tasks like dimensionality reduction, anomaly detection, and denoising. As an extension, we applied an ensemble method combining the predictions of multiple individual models to produce a more robust and accurate final prediction. The ensemble approach can help in capturing diverse patterns of attacks, reducing overfitting, and increasing overall model performance, making the system more reliable and effective in safeguarding IIoT networks. Comparison graph of BOT IoT dataset. In this project, we have utilized BOT IoT dataset. Models are compared with the parameters accuracy, precision, recall, and FN score. This is the accuracy comparison graph. On the x-axis, we have accuracy score, and on the y-axis, we have algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positives and true negatives, to the total number of instances. This is the precision comparison graph. On the x-axis, we have precision score, and on the y-axis, we have algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is the recall comparison graph. On the x-axis, we have recall score, and on the y-axis, we have algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the FN comparison graph. On the x-axis, we have FN score, and on the y-axis, we have algorithm name. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. Comparison graphs of MQTT IoT dataset. In this project, we have also utilized MQTT IoT dataset. These are the comparison graphs for MQTT IoT dataset. This is the accuracy comparison graph, this is precision comparison graph, and this is recall comparison graph, and this is the FN comparison graph. Comparison graphs of NSL KDD dataset. In this project, we have also utilized NSL KDD dataset. These are the comparison graphs for NSL KDD dataset with the evaluation metrics accuracy, precision, recall, and FN score. Comparison graphs of UNSW NB15 dataset. In this project, we have also utilized UNSW NB15 dataset. Models are compared with the parameters accuracy, precision, recall, and FN score, and these are the comparison graphs for the parameters accuracy, precision, recall, and FN score. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is model file, which contains algorithm information which will be loaded into the project code during runtime. These are notebook.ipynb file. These are Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. So here I am copying the path. Now open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I am typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flash framework will host the application locally at the default address. This localhost and port, which is this. Now copy this local link provided by the Flash framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flash framework. If we are a new user, we need to register first. So click on sign up button. So here we need to enter all these details to register. But I have already registered. So click on sign in. So here we need to enter the username and the password which we have created and then click on login. We have logged in successfully. So here we need to enter all these parameters, and after entering the parameters, we will predict the attack type. So I'm entering the parameters now. So here I have entered all the parameters. So the first one is service, which is 20. Service is a type of service or protocol being used, that is HTTP, FTP, SSH within the IIoT network data. Flag is 9. Flags in network packets indicating status or control information. Example SYN, ACK, FIN during communication. SRC bytes is 491. Number of bytes sent by the source in a network communication. DST bytes is 0. Number of bytes sent to the destination in a network communication. Count is 2. Frequency of number of occurrences of a particular network event or activity. Error rate is 0. Rate of connection attempts that resulted in an error at the source. Same SRV rate is 1. Rate of connections to the same service has the current connection. Different SRV rate is 0. Rate of connections to different services than the current connection. DST host SRV count is 25. Count of connections to the same services as the destination host. DST host same SRV rate is 0.17. Rate of connections to the same services as the destination host. DST host different SRV rate is 0.03. Rate of connections to different services than the destination host. DST host server rate is 0. Rate of connections attempts resulting in errors at the destination host. After entering all these parameters, click on Predict button. These parameters represent various features or characteristics extracted from network traffic data within an IIoT environment. They serve as crucial indicators or attributes used by deep learning models to detect and classify potential attack activities or anomalies within the network. Analyzing these parameters helps in understanding network behavior, identifying patterns of normal and potentially harmful activities, and subsequently training models for threat detection and security purposes. Now click on Predict button. So here we can see we got the result. There is no attack detected and it's normal. Now we will enter another set of parameters and check whether attack is detected or not. And if attack is detected, what type of attack is detected. So I'm entering another set of parameters now. So here I have entered the parameters again. Service is 0, flag is 0, SRC bytes is 123, DST bytes is 1, count is 0.05, server rate is 0.07, same SRV rate is 26, different SRV rate is 0.1, DST count SRV count is 0.05, DST host same SRV rate is 1, DST host different SRV rate is 1, DST host server rate is 1. After entering all these parameters, click on Predict button. So here we got the result. Attack is detected and it's DOS attack. Now we will enter another set of parameters. So I'm entering another set of parameters now. So here I have entered another set of parameters. Now click on Predict. So here we can see we got the result. There is no attack detected and it's normal. In this way, by entering the parameters, we can predict whether attack is detected or not. And if attack is detected, what type of attack is detected. Now click on Sign Out. The conclusion of the project is, the findings suggest that deep learning models developed for identifying harmful attack activities within Industrial Internet of Things IIoT systems have yielded positive and encouraging outcomes. This implies that these models have shown effectiveness in detecting and classifying potential threats or anomalies within the IIoT network data. The project employed deep learning techniques, specifically deep autoencoders and feed-forward neural network (FFNN), to process and analyze data obtained from TCP or IP packages. These algorithms were likely used for feature extraction, pattern recognition, and learning representation from the network data to identify potentially harmful activities or anomalies. The methodology employed in the project has resulted in a decreased rate of false positive identifications, misclassifications, and an increased accuracy in detecting harmful attack activities compared to previous methods. This indicates the robustness and reliability of deep learning models in distinguishing between normal network behavior and potentially malicious activities within IIoT systems. The utilization of deep autoencoders, a type of unsupervised learning model, has enabled the successful identification of abnormal or anomalous behavior within the IIoT network data. Additionally, these models have potentially facilitated the optimization of settings or configurations to enhance the detection and response mechanism for potential threats or attacks in IIoT environments.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.